38, something like, and 37 have, okay, 38. Everybody seems to have written their name in the Zoom chat. All right. So what we are going to do today, and I can, yes, indeed, I will stop my video to stop myself from distracting myself. Let's see. Can we do that white? Yes, it works. Very good. Very good. So we can start our work. So last time we were talking about the scalar product of two vectors. We were talking about the scalar product, and that was something else. I'm going to write on this very screen at the moment. So the scalar product or the dot product was if we had two vectors, let's say vector A, okay, this is nothing, it doesn't exist, and vector B, then the scalar product could be written as the products of the corresponding components or projections or coordinates, and then these products were simply added up. We had a lot of properties for the scalar product, but the thing is that the scalar product was a number, and it can be found rather simply from the coordinates of the two vectors. Now, the vector product is something else. The vector product is something else. The vector product, as the name says, is a vector, it's not a number. So the definition, suppose we have two vectors with coordinates, as always. So the vector A has coordinates ax, ay, az, and the vector B has coordinates, and the vector B has coordinates bx, by, bz. Okay, let me just put that there. All right. Now, if we want to do the vector product, the vector product is defined. The vector product is defined as the vector, so that's important. It's not a number, it's a vector. It is written with the cross sign, the cross product. That's why we always call it also the cross product. It's a bit shorter than to say the vector product of two vectors. It's simpler to say the cross product or the vector cross product. So now the interesting thing, let me see. Okay, we find it like this. So you see, we have a determinant. The first line consists of the base unit vectors, as you see, I, j, k, in the first row of this determinant. The second row is the coordinates of the vector A, ax, ay, az, and the third row are the coordinates of the vector B, bx, by, bz. What this means is, of course, that we multiply the vector I by the minor or the cofactor, and that would, okay, just a moment, I think I still have to adjust the new, okay, let's do it like this. So we can write the vector product would be evidently the vector I times the minor a y a z b y b z. Now remember we had a minus, it was the minus position, the base unit vector j is in the minus position for the determinant, and here we have the minor ax, az, bx, bz, and we have plus the vector k times its minor, which is ax, ay, bx, by. This is a bit long to remember, of course. I realize very well that this is something. This is, if you want to write it as a single formula, you could of course also open these determinants. But in principle, what we see is that the vector product is a vector whose coordinates are the cofactors of the elements of the first row of the matrix, of the determinant. So we could say that the vector product is actually the vector that has coordinates these determinants, these minors. So it would be, again, I will not rewrite them, but evidently we have these cofactors. That is, the second cofactor involves the minus sign, minor with a minus sign. So I'm not writing the actual repetition of the same coordinates in there, but I will basically indicate things. I'm not exactly sure what is it that is detaching itself from my computer. All right, so we have this vector product. Let's note that this is a vector. Again, I am stressing it. So it is really imperative that you do not confuse these two products, these two things. So I'm repeating that the dot product or the scalar product is a number, let's say a scalar, it's a number, but the vector product is some vector. So there's a huge difference. And also the way we compute all those numbers, all those things, there's also a huge difference. And of course, let's remind you again that the cross notation, the notation is different, and the notation is very important if we want to distinguish these two products. And of course, the properties are very different, and the applications of the vector product are also very different from those of the scalar product. So here we have a new definition. Perhaps we need to use some examples. So let's suppose that we have two vectors, vector A minus 1, 2, 3, vector B with coordinates 4, 0, minus 5. Let's find this vector product A times B. Let's find this vector product A times B. So formally, we write A times B equals, now the determinant, the base unit vectors I, J, and K, the coordinates of vector A, minus 1, 2, 3, and the coordinates of the second vector B, 4, 0, minus 5. Let me note, I will stress it once again later. Let me just note that if, remember from the determinant properties, if we exchange two rows in a determinant, not in a matrix, not matrix methods, not for Gauss method, but in a determinant, exchanging two rows causes the determinant to change sign to the opposite, which means the order of the vectors A and B in which we write them is important again, because if I wrote B times A, if I took vector B in the second row and vector A coordinates in the third row, the determinant would be with a minus sign in front now. The determinant would change the sign, so the vector C would change its direction. We will see it a little bit further. So for now, I'm just stressing the importance of writing these two rows, row 2 and row 3, in the correct order. And so we might write that this is the vector I times the minor, evidently 2, 3, 0, minus 5, minus vector J times the minor, minus 1, 3, 4, minus 5, and plus vector K times its minor, minus 1, 2, 4, 0. With a little bit of experience, of course.
Miss, I have a question.
Yes.
So what will be the vector product of a 2D vector? But it's a 3D vector, right? So what will be the...
For two-dimensional vectors, I will come back to this. I will come back to this when we see the description and the properties of the vector product. We will see what happens when we have two-dimensional vectors. In fact, vector product is something that leads us into the third dimension always. Always. It actually goes into the third dimension. And so let's see the coordinates. Let's see the coordinates, because evidently with 2 dimensions, it might not work like that. Actually, it's by definition, by default, it is a 3-dimensional enterprise. Okay, so we have minus 10 I, and here we have 5 minus 12. So that would be minus j times 5 minus 12 is minus 7. And plus k times 0 minus 8, so that would be times minus 8. So we can write minus 10i plus 7j, the sign is changed, minus 8k. Or we can in fact think of the vector immediately in terms of coordinates. We don't have to write them with ijk. We can immediately write this vector actually using only the minors without the ijk, because that's faster. And so the coordinates of this vector, minus 10, 7, and minus 8. So I'm reminding you once again that for j, for the vector j, we need to change the sign. So this means, yes, we have to change the sign. Here, the second vector, because it's the minus position. Remember, plus, minus, plus. Okay. So this is the vector product of the 2 given vectors. So that would be our vector C. Actually, in fact, it is possible to think of these 2 vectors when we multiply them. It is possible to think of them, think of the product in a vertical form in some sense. For example, I could write the 2 vectors, vector A minus 1, 2, 3, vertical form, times vector B, which is 4, 0, minus 5. I'm doing the same thing, just using a different kind of writing, which is also very possible. And now, if we do it vertically, then in the first position, we need the minor of the first position. That is, just pay attention. If you just look at this, the minor for the first position, we imagine that we cross out that first coordinate. So for the first coordinate of the product, we use the minor consisting of the other coordinates of the 2 vectors. So for the second coordinate, we write a minus, of course, because the sign changed. For that second coordinate, we can imagine that we cross out the second coordinates and write the minor constructed from the first and third coordinates. And to find the third coordinate, we think that, okay, perhaps we could cross out the third coordinate and write the minor consisting of the other coordinates, minus 1, 4, 2, 0. You see that basically those minors are the same. The minors are exactly the same. They might change. You see, they might be switching the rows and the columns. So in a way, these would be the minors, the 2 second-order determinants of transposed matrix. But you see, the value will be the same. 2 times minus 5, 0 times 3, subtracted. Minus 1 times minus 5, minus 3 times 4. So we see that even the order in these minors looks a little bit different because the rows and the columns are exchanged. But the values of these minors will be exactly the same thing. So this would be another approach, another trick of how to multiply 2 vectors cross product efficiently and as quickly as possible. So I would say writing this is not the fastest way. I would say that perhaps understanding how we construct these minors is faster, or just writing these minors with the appropriate including the minus sign, the cofactor using the remaining coordinates. And to find the third coordinate of the product, you delete the third coordinates of the given vectors and write down the minor using the remaining numbers. That's actually a very simple approach to finding a vector product quickly. Now for the second part, A times C and B times C, but please note these are dot products. These are scalar products. So this would be the old approach. So I would say A times means I need to multiply, I could say vertically again, why not? -1, 2, 3, dot, because this is a dot product, times the vector C, which is, as we saw, -10, 8, -7. And remember how we found the scalar product by multiplying the corresponding coordinates and adding them up. So -1 times -10 is 10, plus 2 times 8 is 16. Wait, something went wrong. -1, 2, 3. Oh, okay, I confused the numbers. That's right. This is why I copied the numbers wrong. It's the other way around here and the other way around here. I was looking in the wrong place. Sorry. So this was actually 7, this was -8, this was 7, and this was -8. So that makes more sense now. So erase, come on, eraser, erase this, and you get things right. So 10 plus 40, 2 times 7, and 3 times -8 is -24. It is 0. It had to be 0. We will see in a while. Why and how it happens. And B times C, vector B dot C, again, the same. Vector B is 4, 0, -5 times 10, -10, 7, -8. And we have -40 plus 0, and -5 times -8 is plus 40. It's again 0, which presumes the conclusion from this. Remember the scalar product properties. This seems to be stating that the vector A and vector C are perpendicular, and vector B and vector C are also perpendicular. That is, the vector product is perpendicular to both the given vectors in some sense. Let us see. We could, at this moment, of course, you could say, but that's a coincidence. You just picked those vectors A and B so that this happens. Well, that's not exactly the case. This is a rule, and this can be proved, in fact, if we open up everything, if we use the expansion of the determinants, if we write down the things down very carefully, we would see that it's possible to prove this is always the case. This is always the case. Let's see what's coming up next. Okay, all right. I actually happened to have forgotten that I put that determinant there and then just went on working with it. So I am erasing what? I am erasing this part that is copied by my determinant that was printed. Okay, it's this. I was writing it. I did write it by hand, but I always also had it printed. Now the properties of vector product. The properties are actually very, very interesting. Let's start with the first one. Geometrically, as we saw, if the vector C is the vector product of the two given vectors, then it is perpendicular to each of those two vectors. Let me see if I have the picture. Included. Yes, I have it. So see what happens. If we have the two vectors A, B, of course they can be written or actually sketched from the same starting point, so vector A, vector B, and here we have the angle, we can call it theta or we can call it alpha, whatever. And then what happens with the vector A times B is that it is perpendicular to each of these two vectors. In other words, if the vectors A and B, as you noted, are in two dimensions, that is, the z coordinate of these two vectors is 0, we could say. So we could say if I have the two vectors, vector A, let's say 2, 3, and vector B, let's say -1, 4, then to find the vector product, we simply think, okay, it will be a three-dimensional situation anyway. It will be a three-dimensional situation anyway, so I will simply attach a third coordinate 0. Let's say the z coordinate is 0 because these two vectors are in the xy plane. And when I multiply these two vectors, this will go out into the third dimension inevitably, because for the third coordinate, if you delete those zeros, for the third coordinate, you will generally get a non-zero number. So the third coordinate will not be 0, which means the product vector does go out of that plane. Just if we just try this, then A times B, for example, in this is just an example. So the first coordinate would be 3 times 0 minus 0 times 4 is 0. That's interesting. The second coordinate would be minus 2 times 0 is 0, minus 1 times 0 is 0. It would still be 0 if you find the minors. I'm not writing out the minors at the moment. The third coordinate, however, will be 2 times 4 is 8, minus -3 is 11. And so you see that this vector A times B is actually strictly vertical. It goes strictly in the z direction only. So A and B are in the xy plane, but the z vector, the third vector, the vector product, is inevitably it goes out into the three dimensions. And what's more, it goes perpendicular, I'm very sorry, parallel to the z-axis, but perpendicular to the xy plane. So this might be an answer probably to the question, what happens if we have two-dimensional vectors? Then we can think, okay, they are in the xy plane, we attach the third coordinate, and we see that the vector product must go out of that plane. All right, now let's go on. The vector system ABC is right-handed. What does that mean? A right-handed system means that when we go from A to B to C, that already happened when we were actually considering the three-dimensional coordinates for depicting vectors. Remember, we had this three-dimensional system in which we depicted the endpoint of the vector. So what happens with the right-handed system is, if I go from A to B, then from B to the C, then from C back to A, through the smallest angle, evidently, then we go in the positive direction, counterclockwise. Or you could say that if you, for instance, if you want to screw a screw somewhere else, or if you want to turn on the volume with an old-fashioned knob, you know, the old-fashioned knob that you are actually turning to arrange something, or you are screwing a light bulb. So nowadays, everything is just click in place, not so much about screwing things in, but still, if you are screwing the screw in the correct direction, that is as you do it with the right hand, the right screw, then it goes up. Imagine that you are screwing from A to B in the XY plane, so the screw goes upwards. as it moves. So the right screw, the right-handed system, screwing in the light bulb. If you screw the light bulb in the direction from A to B, it moves up. So that's the right-handed system. And so there we have it. So we see now that what happens if we go from B to A, the direction has to change then. The direction has to change then. We will have it in a while. At the moment, the magnitude, because a vector, as you know, a vector is defined in some sense. We could say the vector is defined if we know the 3 coordinates of it. Yes, the 3 coordinates are there. But the vector could also be defined if we know the direction. Exactly, that's the first rule. This first property tells us what is the direction of the vector product. And now the magnitude, so the direction and length. Then we can say the vector is defined. So the magnitude of the vector product is again something quite interesting. It's a formula like this. The magnitude is magnitude of A times magnitude of B times sine of the angle between these two vectors. It could be theta, but I will actually change this to alpha. Let's make it alpha. That's a simpler thing. It's not the letter A, it's alpha. It's the Greek alpha. So
Miss, I have a question. So, Miss, if we multiply B times A, will it be minus C?
Yes. Yes.
Okay.
Yes. Now the magnitude. I will have this property in a few seconds. Actually, the magnitude A times B, magnitude of A, magnitude of B, and sine of the angle between the two vectors. Remember that the scalar product, interestingly, the scalar product. This is a similarity, and therefore it is actually quite important not to confuse things. So for the scalar product, we can compare. The scalar product is actually length or magnitude of first vector times length or magnitude of the second vector times the cosine of the angle between the two vectors. And the vector product is not magnitude times sine, but this is simply the length. So the scalar product is it already. It is the scalar product, this thing. But for the vector product with the sine, it's only the magnitude because we do not have a number, we have a vector. But yes, there is a similarity, and this is even more important that you do not confuse. So I cannot stress it enough that you should never confuse the dot product and the cross product, because they are two very different things, and they have very different meanings, in fact. So the magnitude actually involves the sine of the angle alpha. We know that the sine of an angle, which is anything between 0 and 180 degrees, the sine is positive. So in fact, the length does not depend on the order, whether we go from A to B or from B to A. The angle between these two vectors will be not important because we are actually measuring the angle as it is, not looking at the direction, positive or negative angle anyway. But the idea of negative changing sign, that is this anti-commutative property. If I have vector A times vector B, it is the exactly opposite to vector B times vector A. Exactly that. So if A times B is C, then B times A is minus C. If you exchange the order, if you simply swap the two vectors, B times A, you get the opposite determinant. Remember, the determinant also changes signs when we swap two rows. So this makes sense. And also here, from these properties, we can imagine if I had vector B first and go to A, then imagine the screw. If we turn this screw from B to A, the screw goes down. So the vector will go downwards. So this would be the vector B times A. Exactly the opposite. exactly the opposite. Because then we would go like this in the opposite direction from B to A. Associative property, how do we deal with numbers? Exactly the same way as we deal in the scalar product. So the associative property is exactly the same. You can multiply by a number, one vector or the other vector or the whole vector product at once. This is from the determinant properties. Remember, when you multiply one row by a number, the whole vector the whole determinant becomes k times greater. Or if you multiply another row by that number, the same thing happens. In other words, in fact, you can think that I can take the common factor k from the row and bring it out in front of the determinant, just like we did with determinants. So this can be explained using determinant properties. Also, it could be explained using the length of vectors. Okay, eraser, come on. Erase this. Next. Distributive property. Yes, again, just like with the scalar product, you can open the brackets. But like with matrices, just like with matrix product, you have to be very careful about the order of multiplication. Remember, for matrix product, when we multiplied matrices, you could also open the parentheses and multiply them. But the matrix product was dependent on the order of the matrices you put there. And in the same way with vectors, it's also important that if you have A plus B times C, then it's A times C plus B times C. Or if you have, I don't remember, no, if we have C, okay. Why does it do it? I would like to write to this other version as well. C times the sum A plus B then must be written as C times A plus C times B. Because the order of multiplication is important, the sign of the vector, the direction of the vector might change otherwise. Now, okay, what happens if two vectors are parallel? If two vectors are parallel, so now let's think about this sign property, about this thing. So let us take something bright again. For this, from this we can say, if vector A and vector B are collinear, then the angle alpha is either 0 or 180 degrees. For parallel vectors, it would be 0, same direction. For anti-parallel vectors, it would be 180 degrees. But in both cases, sine of this angle is 0. So this means that if two vectors are collinear, that is parallel or anti-parallel, then the vector product is the 0 vector, because the magnitude, you see the magnitude would be 0. But it's the 0 vector. It's not the number 0, it's the 0 vector with 3 coordinates. 3 coordinates. All 3 coordinates would be 0. And if the vector product is 0 vector, it means its magnitude is 0. This means the sign has to be 0. This means alpha has to be either 0 or 180 degrees. So this is if and only if. However, we do not use this to check parallelity. We do not use this to check collinearity of two vectors because it is too messy. Then you have to find 3 coordinates. You have to find 3 minors, 3 determinants. You have to check that all 3 determinants are equal to 0 before you actually say that the two vectors are collinear. And that's too much. It's much easier to use the proportion. Remember how we checked collinear vectors? We checked using the proportion. Where am I? I'm here. We checked the collinearity using this proportion. AX to BX, AY to BY, and the third ratio, AZ to BZ. These three ratios must be identical. So proportion. This is for collinearity. This is for testing for collinearity. Testing for collinearity. We do not use this sixth property for testing anything. We only use it for algebraic purposes when we need to eliminate some elements from a product, from an expression. Then we can actually use the fact that the vector product of collinear vectors is the zero vector. For testing, for figuring out, is there parallelity, or for finding for what value of M are the two vectors parallel, we use collinear vectors. Will you use this test with proportion? Because this is much more efficient. It is faster, it is simpler, it is easier. And finally, looking at the unit vectors, if you look at the base unit vectors, let's draw them. This is the base unit vector K, this is the base unit vector I, and this is the base unit vector J. Three vectors in perpendicular directions, each is 1 unit long. Then let's see, judging by this diagram from the directions of the vectors, I times J has magnitude 1, because the vectors are perpendicular. The vectors are perpendicular, that is, sine of the angle is 1. The magnitude of the product is 1, and it's perpendicular to both vectors I and J, right-handed system. So I times J evidently is the vector K. Perpendicular to the plane IJ, the length is 1, because sine of the angle between I and J is 1. Similarly, JK, if you screw in the direction from J to K, you can imagine that the screw goes in the direction of I, and similarly, again, the magnitude is 1. And then from K to A, we get J. It's not alphabetical, it's cyclic. You think in terms of a cycle. From I to J, from J to K, from K to I, and so on. So the direction in which we think about these three vectors is always corresponding to that cycle, going in the positive direction, anti-clockwise. So it's not I times K, it's K times I, if you think geometrically in the positive direction, always going in circles, as you can see, always screwing things in. So basically, the right-handed system means screw it in, go from A to B, and the screw goes in the direction of C. These are the properties of the vector product. And here we have applications. Now, it would have been nicer if I had remembered to put the exercise here, but never mind. Let's see the applications. And after we see the applications, we will have examples. And so, first, to find a vector that is perpendicular to each of two vectors. Do we have? No. How do we do that? So a vector, of course, if there are other properties that must be observed, we need also take this into account. But basically, this is where the vector product actually comes from. Originally, if I have two vectors and I need to find a vector that is perpendicular to each of these two vectors, I can attempt to solve a system. So let's try some example. For example, let's say, yes, Torque, exactly. torque, the moment of force. That's exactly it. We will use, yes, the torque is actually the last application for this. So let's suppose we have the vector A, for instance, 1, 2, 3, and the vector B, let's say 2, 0, minus, I don't know, 4, let it be. So we can say that one vector, let's say, perpendicular to both. So I want to find some vector n, which is perpendicular to A and perpendicular to B. So one such vector is very definitely the vector A times B. Another one would be B times A, for example. Like this, and we can do it using the vector product. And that would be, now let's see, to find the first coordinate, we pretend that the first coordinate is not there. So we would have 2, 3, 0, minus 4. To find the second coordinate, we cross out the second coordinates, put a minus in front, and we have 1, 3, 2, minus 4. And to find, what is that? What is that? Something, okay, something like this. Oh, right. Why did it lose my color? I don't know. Okay, now it is there. And the third coordinates eliminated will give us the minor 1, 2, 0, which is minus 8, minus 0, minus 4, minus 6 is minus 10. Change sign, we get plus 10. And 0 minus 4 is minus 4. That is one vector perpendicular to both. Of course, we can see that we could take a vector that is two times shorter than this. We could divide all coordinates by 2. So this is only one vector that is perpendicular to both of them. So sometimes I might say, find the unit vector that is perpendicular to A and B. For that purpose, I would need to find the length of this vector, magnitude, and divide this vector by the magnitude to make a unit vector, for instance. There might be other things. So this is one of the vectors. Well, at another note, we might say that if this vector, unknown vector C, if this, okay, let's say it's C, we found this C as the vector product. But if this unknown vector N has perhaps coordinates X, Y, Z that we do not know, then for perpendicularity, I would say I need the product N times A to be 0 and N dot product times B to be 0. Then I can say that the vector N is perpendicular to both A and B. So that would be 1x plus 2y plus 3z must be 0. That is this product, the first one. And for the second product, I would have 2x plus 0y minus 4z equals 0. And then when I attempt to solve this system, actually, I get some very interesting things. I could say, for instance, if we take z equal to some constant t, for instance, if we take z is t, then x is something else, and then we can actually solve the system using, for example, Gauss method. The solution of this system would be something using parameter, using c. It could be, for example, something like c, and then we would have 2c, and then we would have another vectors that would be minus 2.5c. For example, we could actually solve this. We could actually solve this system. This is easily solved. So I can in fact see how this works out. So x is actually equal to 2z. From this, we could say, see, x is actually equal to 2z from this. So if z is c, then x is 2c. And then when we put X and Z as 2C and 3C in there, we would actually get the coordinates that are, let's say, collinear to these. So basically what this amounts to, why I'm talking about this is where the vector product actually comes from the need to sometimes be able to find a vector that is perpendicular to the two given vectors. So we could do it this way, which is the long and messy and complicated way, or we can do it by this method, which is simply finding the vector product. And this is, let's say, where historically the vector product comes from, how it actually connects to the whole idea, because otherwise you would say, who invented this vector product? Why would we need this vector product, this very strange thing? So the answer is actually we need it whenever we need to find a direction that is perpendicular to each of the two vectors. For example, as we say for physics, it's the torque. Then next, to find the area of a parallelogram, if A and B are the vectors defining adjacent sides. That is, suppose we have this parallelogram, and the vectors A and B define adjacent sides. And the angle between alpha would be, the angle between these two vectors would be alpha. Normally, now this is a little bit tricky because some people think, okay, so we need to find the A length, B length, and the angle alpha to find the area of the parallelogram, because we know that this basically is the area of a parallelogram. The side times the other side times the sine of the angle between these two sides. That's by definition from school. That's from school geometry. The length of A times the length of B times sine of the angle. So this is from geometry, the area of the parallelogram. However, if we just have the two vectors A and B given by coordinates, it would actually take a lot of effort to find the length of A, the length of B, then using cosine, finding the cosine of alpha, then from cosine of alpha, getting the sine of alpha, and then getting the area of parallelogram by geometrical definition. This is where the vector product makes it very short. You find the vector product, simply multiply the two vectors using the coordinates of A and B, find the magnitude using the Pythagorean theorem, and that will be the area of the parallelogram numerically. Sometimes people ask, what has the length of the vector C of some vector? The length of one vector cannot be the same as the area. The length is the length, right? Vector C. Length is length and area is area. They are completely different ideas. They are completely different things. The units of measurement are different from, for example, meters and square meters. So the thing is, exactly, the length is not the area, but numerically, number-wise, the value, only the number is the same. I'm not saying that the length is the same as the area. It's not. But the number, the value is the same. The numerical value is the same. You can imagine that the length of C is actually, for example, the area of a parallelogram, let's say unit vector in the base plane and the perpendicular vector length C. You could even think about it like this. See the length of C as an area of a rectangle length C and width 1, which is not exactly the case, but you can imagine something like that. If you really don't like the idea of length and area being the same, and of course they are not the same. Of course, they are not the same things. So we will do exercises for this as well. Next, the area of a triangle evidently is half of this, because a triangle is half of a parallelogram. So if we have a triangle, again, built on two vectors, A and B, as you like, we can actually imagine that we complete the picture to a parallelogram. That's basic geometry. And that means that the area of the triangle we can see is half of the parallelogram, half of the area of a parallelogram. This is simply a very simple consequence of the previous one. These two properties, these two applications are very, very important, because basically what we think is we find the vector product. We don't mess around with other things. We actually simply compute the vector product, and that is the simplest way we can achieve these two tasks, and also the third task, of course. In physics, if force F is applied at the point A, then the moment of force, or torque, and some of you have studied that in physics, of course, equals the vector product of F and the position vector. And imagine this torque thing. Torque is something about turning, about rotation. So you can understand why I was using this comparison with a screw. Actually, in physics, when you talk about forces, torques, and other things, they do use the idea of screw, the right screw, sometimes the left screw, quite a lot. And so if we have the origin of coordinates, we have the point A, we have the force applied to this point A in some direction, perhaps. Then actually we see that the moment of force, the moment of force, torque, is F times R. F times R. R is this displacement vector, the vector product. And now to the examples. Let me check the time. Oh yes, there's enough time for many examples. So let's see. Suppose we have three vectors. Actually, I should put them more understandably. I would say the vector P is 2, 0, 1. The vector Q is 1, minus 2, 1. And the vector R is minus 2, 4, minus 3. Then let's find some vector products and some values. So we have 8 things to find. In fact, it's not 8 completely different vector products. There are not so many. So let's see, vector P times Q. Let's do A. Vector P times vector Q is evidently 2, 0, 1. Times 1 minus 2, 1. This is a very simple way of doing it. First coordinate, we eliminate the first coordinates and think 0 times 1 minus 1 times negative 2. So that 0 minus negative 2 is positive 2. For the second coordinate, eliminate second row, second coordinate, and you have 2 times 1 minus 1 times 1. That's 1, but change the sign, so it becomes minus 1. And similarly for the third coordinate, eliminate the third coordinates and look at the remaining minor. Okay, I would actually try to use the pointer. So when I'm finding the first coordinate, I just cross out, eliminate the first coordinates and look at the remaining determinant. When I'm finding the second coordinate of the product, I think eliminate the second coordinates and use these remaining elements, and don't forget to change the sign, because the J coordinate, the second coordinate needs to change the sign. And finally, I am eliminating the third coordinates of the given vectors. Of course, all the elimination takes place in your mind. And we have 2 times minus 2 is minus 4. Minus 4 minus 0 would be still minus 4. This is the vector P times Q. Now be vector Q times P. Should we do it all over? Well, probably not. Just remember the properties. Q times P is actually minus P times Q, which means it's the opposite of this vector. It's minus 2, 1, 4. If you prefer, you can write these vectors in the horizontal form. It's just that multiplication is very simple in this form. However, if you want to multiply them horizontally, you should not write a determinant as if consisting of only 2 rows. Then it's perhaps better to write the 2 vectors one below the other as they are. Just don't write a determinant which is not square. C, P times R magnitude. So for that, first of all, we need to find P times R. So if you want to find P times R, you could also write these 2 vectors one below the other. So 2, 0, 1, and R is minus 2, 4, minus 3. Vector P, vector R. And the product, P times R, P times R, the product would be, now you can think. For the first coordinate, eliminate the first coordinate and you get 0 times minus 3, that's 0, minus 4 is minus 4. Second coordinate, eliminate second coordinates and you get 2 times minus 3 is minus 6. Minus 6 minus negative 2 is minus 4, but change the sign, it becomes plus 4. And for the third coordinate, eliminate third coordinates and you get 2 times 4 is 8. And minus 0, it's still 8. So the absolute value, the magnitude of vector P times R as required would be the square root of 4 square plus 4 square plus 8 square. That's 16, 16 and 64, that's 96. Square root of 96. 96 is 6 times 16, that is 4 square roots of 6. That's the absolute value of P times R. D, R times Q. R times Q. Again, absolute value, that means we again have to do this. R times Q. All right, vector R is minus 2, 4, minus 3. Vector Q is 1, minus 2, 1. Here you can see the minors very clearly. So vector R times vector Q is, as we see, again, I will again take the pointer. So if we eliminate the first coordinates, the remaining determinant will be the first coordinate of the result. If we eliminate the second coordinates, the remaining determinant with opposite sign will be the second coordinate of the product. And if we eliminate the third coordinates, then the remaining numbers, the remaining determinant will be the third coordinate of the product. So we think in terms of eliminate those coordinates in the given vectors and in the product, and in the product you will have this. All right. Next, we have to do this. So 4 minus 6 is minus 2. Middle coordinates eliminated. Minus 2 minus negative 3 is 1. Minus 2 minus negative 3 is 1. Minus 2 plus 3. But sign change for the second coordinate always. And finally, the third coordinate's eliminated. 4 minus 4 turns out to be 0. And so the absolute value, the magnitude of this product is square root of 4 plus 1 plus 0, that is square root of 5. So in fact, yes, in fact, what we would see here in this case is that square root of 5 would be the area of the parallelogram built on these two vectors. So what in fact we find when we compute these values C and D, if I have the vector P and the vector R, and if we imagine that the parallelogram is built on these two vectors, then if we multiply these vectors, if we find the cross product of these vectors, and then the magnitude of this cross product, then this number would actually be the area of that parallelogram. This is how we use it for parallelograms. Now next, E is, all right, E. 2 vector P times 4 vector R. Remember the number property? We can take 4 outside of the vector product, and we can take the number 2 outside of the vector product. So I can actually say that this is 8 times P times R. And P times R is something that we already have. We have it here. So this would be 8 times the vector minus 4, 4, 8, minus 4, 4, 8. And that is, we have minus 32, 32, 64. And that's it. We didn't have to multiply the vectors by numbers and multiply them again, because we already have what we need. F. Let's see. P plus R times R. P plus R times R would be P times R plus R times R. Now let's just remember, a vector multiplied by itself means multiplication of 2 parallel vectors. Remember that the product of 2 parallel vectors was the 0 vector. So in principle, this is P times R vector plus the 0 vector. P times R vector, where are you? Oh, it's still the same. It's minus 4, 4, 8. And that's it. So if we use the properties cleverly, then actually we don't have that much to do. We can actually save ourselves some work. So I'm going to get rid of this. I'm going to get rid of this because this was simply an example, an explanation about the areas, not a part of this exercise directly. G. Let's take G. G, P times Q times R. P times Q times R. We can do this in order as written, Q times R, or we can write it P times Q times R. We can actually change the order of multiplication, but because that property was not stated explicitly, let's do it as it is. So the vector P is 2, 0, 1. Vector Q times R. See, vector R times Q was this. So vector Q times R is the opposite of this vector that we have. So I would actually write the opposite of. No, I will write it slightly differently. Okay, a pity that erasing things takes that much special time. Not something. Okay, times minus R times Q. Let's put it this way. And so I have 2, 0, 1 times R times Q is minus 2, minus 1, 0. The opposite vector would be 2, 1, 0. And so we have 0 minus 1 is minus 1. 0 minus 2 is minus 2, change sign is plus 2, and 2 minus 0 is simply 2. Or minus 1, 2, 2, whichever way you like it to write it. And finally, the last one, H, P plus 2Q times R is something where we open.
Minus 1.
What one? Where? Which part? Okay, there. P, let me see. The vector P, I need the vector P in the vector P 2, 0, 1. And in the vector, wait. Oh, you mean this 0 minus 1? No, 0 minus 1. See, 0 minus 1. We subtract. So it's not plus 1, it's minus 1.
Right, I understand. Yeah, because it's determinant. Yeah.
Yeah, it's determinant. It's because it's determinant. And now, opening the parentheses in H. Opening the parentheses in H, we have P times R, which is good because we have it, plus 2 times Q times R, which is very good because we have it. P times R, where we have it, okay, it's this. So it would be minus 4, 4, 8, plus 2 times Q times R, that was this vector. Wait, just a moment. Minus R times Q, it was plus, but it was plus there, right? It's everything's correct. I saw, it looked like a minus. It's actually, it was part of my line. So the vector Q times R is 2, 1, 0. From the previous, we already have the vector Q times R. And so we have minus 4 plus 4 is 0. 4 plus 2 is 6, and 8 plus 0 is 8. So we see that, well, it's not always, you won't always have a huge task like this. This task was specifically designed for practicing the properties so that you can use some previous results sometimes to simplify the process. But in general, that simply means that if you can apply a property to simplify something, then do it. If it simplifies something. If it does not simplify anything, then there's no use to use that application, no use to using that property. But if it does simplify the situation, then we should use it, as we did it with quite good results in this particular exercise. All right, so this was simply practice of properties. Next, find all vectors that are perpendicular to both these two, A and B. So one possible way would be, let's say, solving a system, saying, okay, vector perpendicular to A and B is, let's say, X, Y, Z. So that would be one method possible. A vector N would be X, Y, Z, that we don't know exactly what exactly it is, but I would understand that 0x, so the scalar products, the dot products, N times A should be 0, N times B should be 0. So this means that the conditions are 0x minus 1 times Y plus 3 times Z equals 0. That's N times A. And N times B would be minus 2 times X plus Y plus 2Z equals 0. So from this, we could imagine using, for example, Gauss method to solve the system. Actually, this system is pretty simple. For example, okay, we could use Gauss method, I suppose. But that's too big a thing for for two lines, for two equations. If I add both equations, I would have minus 2x plus 5z equals 0, which means x is 5 halves of z. From this, we can express this thing, and we can see that y is actually equal to 3z. And this means that I could say, let z be equal to c, and then actually I have a vector that has coordinates 5 halves c, 3 c, c, where c is any number. Where c is any number, well, not 0, evidently, because 0 vector cannot be perpendicular to anything because it's 0 vector. It doesn't have a direction. So c is any real number, just not 0. And so I can take c anything, I can take c anything, and I get all the vectors. So all the vectors can be written in this general form. In principle, we could have used Gauss method, but in this case, I simply saw that this was so easy to eliminate. Y was so easy to eliminate from the second equation that enables us to express both x and y through z. So if we choose the parameter c, some value of c or k or t, call it whatever you like. So all vectors that can be written in this form are perpendicular to both A and B. So that was method A. Method A. So method B would be if we find just one vector, that is vector product A times B is, all right, 0, minus 1, 3 times minus 2, 1, 2 is, and now let us see, eliminate first coordinates. We have minus 2, minus 3, that is minus 5. Interesting. Eliminate second coordinates, you get 0 times 2 minus negative 6, but then change the sign again and you have minus 6. And eliminate third coordinates, pretend they're not a 0, minus 2 is minus 2. Now, if we compare this, basically you can see, yes, if we divide this vector product, let's say C, if we divide the vector product C by 2, by negative 2, then we actually get something like this. So in principle for C, if C is minus 2, we get this value particularly. So I could say that the vector perpendicular to both A and B is any vector in the form, let's say 5k, 6k, 2k. I could write minus 5, minus 6, minus 2k, but what if we simply change the sign of k? So for all k, of course, that are not 0. In principle, this is a little bit better. Actually, if you compare these, if you divide these numbers by 2, if you divide the numbers 5, 6, 2 by 2, you get actually the same. So in fact, we could say that C is just 2 times k, perhaps, in each case. These are very definitely collinear vectors. So if the vectors are collinear, they are, of course, perpendicular to the same plane. They are, of course, perpendicular to the same plane. So it doesn't matter which method we use. However, I would say that finding the vector product is in many cases easier. In this case, we were lucky that we did not have that the x coordinate in vector A was equal to 0, actually. That made this part easy. But if we have all three coordinates in both vectors, if there are no, audio should not be disconnected. Okay, anybody else? Someone is complaining that they cannot hear me. What about everybody else? Can you hear me? Anyone?
Yes, ma'am. Yes, I'm hearing you.
Okay. Then. Okay, sorry. I wrote it to the wrong person. All right. Sorry. sorry. It should be. It's the wrong person. It happened automatically. All right. Okay. Now, so the general idea is that we have to understand if we have one vector that is perpendicular to the two given vectors. If we have one vector perpendicular to two given vectors, then we have infinitely many. We can multiply this one vector by any positive or negative number. We would get vectors that are collinear to this one. And that means they would also be perpendicular to the two given vectors. Therefore, the Gauss method, or this variation of Gauss method, that's why we get this parameter C. That's why we get this parameter C in the vector, because any vector for any value of C would work with this, except for the zero vector. We understand that the zero vector cannot be perpendicular to anything. And on the other hand, if I find one vector like -5, -6, -2, I understand that 5, 6, 2, the opposite vector, will also be perpendicular to A and B. And in fact, any vector which is this times a number. But basically, these two forms correspond to each other. We see that, for example, if we take C equal to 2, we get the vector 5, 6, 2. If we take C equal to -2, we get the vector -5, -6, -2. And that makes sense because this is, in fact, how originally this vector product came into being. That's how mathematicians invented it. All right, next exercise. Parallelogram. A parallelogram, find the area of ABCD, coordinates of D. We actually did this task last week at some moment or before that when we were working on the coordinates of a parallelogram, actually coordinates of vectors. And so, well, if you can hear now, that means the problem was with your computer. Perhaps you had disconnected your speakers or your earphones, some contact not working or something. All right, so suppose we have this parallelogram ABCD. Please remember an extra reminder, because so many people make that mistake. Please make note, A, B, C, D. If the name of the parallelogram is given, the points must be written in the correct order. A, then B, then C, then D, in the same direction. You cannot jump. And so let's see, A has coordinates -1, 3, 2, B 2, 0, 4, C -1, -2, 5, and then the coordinates, which we don't know, we could say X, Y, Z. Remember, there were two ways of finding this. One way was, let's take two vectors and say they must be equal. For example, the vector from A to D must be the same as the vector from B to C. If we have two equal vectors, then, of course, AD and BC, sides of the parallelogram, are parallel and they are congruent, same length. So we could actually say vector AD is point D coordinates X, Y, Z, minus point A coordinates, that's -1, 3, 2, and vector BC, and they must be equal. Vector BC coordinates C, -1, -2, 5, subtract B coordinates 2, 0, 4. And from this we see x plus 1 is -3, that is x is -4, y -3 is -2, that means y is 1, and z is z -2, sorry, z -2 is 1, so z is 3. So this means that point D has coordinates -1, 1, 3. That was one method, equating two vectors. Another method, which I will not repeat, was if we remember that the diagonals of a parallelogram intersect at their common midpoint, you could, for example, try to find the coordinates of the intersection of diagonals from A and C, and then use the coordinates of M to find the unknown coordinates of D, again using the idea of midpoint. That was the first part, part A of this task. Now the area of ABCD, we would understand that, for example, we could have two vectors starting at the same point. Okay, for example, AB, vector AB multiplied by vector AD. We know that AD is the same as BC, so we will use that. And then find its magnitude. So vector AB would be B coordinates minus A coordinates. So 2, 0, 4 minus A coordinates 1, -1, 3, 2. So vector AB is 3 minus 3, 2. That is vector AB. AD we already actually have. That is, these are the coordinates of AD. So in fact, now I can multiply. AB times AD would be 3 minus 3, 2, times coordinates of AD, -3, -2, 1, as found before. And so this vector would be eliminate or ignore first coordinates, you get -3 minus -4, that is +1. Ignore middle coordinates, you get 3 minus -6, that is 9, but have to change the sign. And finally, ignore the third coordinates, -6 minus 9 is -15. So that's the vector AB times AD. Now from there, the area of ABCD would be the magnitude of this vector product. That would be the magnitude of the vector AB times AD. That is 1 square plus 9 square plus 15 square, which is 181,225, which is square root of 300, I do believe 7. So that's the area of my parallelogram. I don't care about the approximate.
I have a question, right? So is it better to use AB and BC to find the area, because we might have an error in
it doesn't matter. Well, it doesn't matter as long as they are not the same vector. They shouldn't be opposite sides.
Yes, but is it better to use AB and BC because if we find the B as a wrong value, it would affect our calculation in part B, right?
Well, I am not using, yes, that's right. But I was using BC. For AD, I was using BC. You are right. If you look at the point D and you start finding the value once again, then you might be mistaken if you look at the point D. But however, I was not looking at the point D. I was looking at the idea that AD and BC must be the same. So I actually used BC, the ready-made one. I didn't go to point D. I went back. I went back to the vector from which we got D. But in fact, yes, you can use the vectors you find more convenient, as long as they are not the parallel sides. As long as they are not the parallel sides. So we can say that, yes, we build a parallelogram on these two vectors, however we place them, but not on two identical vectors, because then the two identical vectors could be anything. So as long as you take two vectors that are non-collinear, not the parallel sides, you can take any two vectors.
Thank you, Miss. Thank you.
Okay, next. Let me check the time. 43, just a couple of minutes. All right. Triangle, area and height. What else? Forces. Okay, there's not so much time. We have to finish. So let us do the forces. The area and height of a triangle, the area of a triangle would be, again, find the vector product, take the magnitude, half of the magnitude, find the base to find the height. So we can actually finish this next time. Let's do the forces. The torque with respect to the point B. What this means is that instead of origin, we take point B, and so the radius vector, the position vector of point A with respect to point B, not the origin, would be, in fact, vector BA. It would, in fact, be the vector BA, the radius vector of point A with respect to point B. That's an interesting thing. So we have to note that the radius vector R is vector BA, and that means from A subtract B, so 1 minus 2. 1 minus 2 is minus 1, 0 minus 1 is also minus 1, and minus 2 minus negative 4 is positive 2. That's one thing. Now the force vector, and we have to multiply force first, radius vector next. So I will probably write the force vector above. So the force vector is, of course, the sum of all three forces. The resulting force, the sum of all three forces. And I will write it right above the vector R. This is not the most comfortable position. I didn't think about it earlier, but because we multiply F times R, I would like, if I write them horizontally, if I write the two vectors horizontally, I would prefer to write them one below the other and in the correct order. So minus 1 and 2 and 3 added, minus 1 plus 5 is 4. Now, second coordinate, 3 minus 2 and 1. 3 and 1 is 4, minus 2 is 2. And third coordinate, 4 and 1 is 5, minus 3 is 2. So the resulting force is this, and the radius vector is this. So now to find the torque, we have to simply multiply these two vectors. So once again, to find the first coordinate, we ignore, okay, that was wrong of me, that was not a good thing to do. We ignore the first coordinates and we simply take the minor using the rest. So 2 by 2 is 4, 4 minus negative 2 is 6. Now, ignoring the second coordinate, and yes, we will need to change the sign, 4 times 2 is 8. 8 minus negative 2 is 10. Change the sign, we get minus 10. And finally, for the third coordinate, ignore the third coordinate, and you have minus 4 minus negative 2. That is minus 4 plus 2, that's minus 2. And that is the torque vector, the moment of force. So it's you simply have to understand which is the resulting force and what is the radius vector or the position vector of A with respect to point B, with respect to point B. So we can imagine that the object A is connected to the point B, and whatever their actual coordinates are doesn't matter, because our center of the world is the point B. And that's why we have to find the vector BA if we want to deal with the vector R. All right. That's it at the moment. Next week, however, we will change times for mathematics and elementary mathematics. I will remind you, and I will put notices in all courses, because next Wednesday we are having the vector test, the vector unit test, and I need all 3 groups to be close together time-wise, and that's why we will, and accidentally, yes, we have a test in elementary mathematics as well. So that's going to be first in the morning at this lecture time, and the regular mathematics at 10:15. So I have to switch those 2 lecture times. All right. I will see you on Friday. On Friday, we will finish up with the vector product with exercises. And there's one more thing to discuss, and that's the mixed product or the triple product of vectors, which is again something. It's not much, but there is this remaining idea. Then next week on Monday, we will already be moving into the next unit, and that is analytical geometry. Maybe we will pick up some loose ends from vectors on Monday as well. Yesterday, I uploaded the home assignment that now you'll have a week to finish it. So basically do whatever you can. There is probably maybe one task, I don't remember exactly, that you might not be able to solve now. One only, but the rest of the home assignment tasks should be solvable at the moment. So you can start working on that in order to practice for the unit test next Wednesday. Okay, so let's finish. I will see a few of you for the elementary mathematics. I would like to remind people who are not attending elementary mathematics, you are playing with fire. I will not allow you to take any examinations, and you will fail the whole course of mathematics. There are quite a few people who must take elementary mathematics and who are not attending. That's not going to end well. All right. So I'll see you in 25 or something like that minutes. And the rest of you, I'll see on Friday.
Excuse me, ma'am.
Okay. Yes?
Ma'am, is recording available for the last few lectures?
One recording was somehow, I found it was very, very small. In the link I saw there were not enough megabytes. So I think one of them is spoiled. One of them is ruined. One of them is incomplete. But the rest of them seem to be in order.
Where can we find it?
You cannot. You can ask me and I will send you. I have to do something to force you to listen during class, because I know very well there are quite a few people who write their names, go away from the computer, leave the computer open so that I think that they are there. They don't listen, and then they ask for recordings.
Ma'am, I was not able to hear. That is why I wrote you.
Okay. Yes, if you are not able to attend, then please email me and I will send you the recording. And that's it. And that's simple. I simply object to people being able to freely access recordings. That means they don't attend lectures. And that's not the thing. If you were all here in Riga, you would be required to be here on the spot. So please be here in the lectures if you can. If you cannot, things happen. Yes, you can let me know and I will send you the recording. But those are exceptions. This is not the system. All right. Okay. All right. So yes, the recording will be available. The recording will be available to those who have missed this lecture. Yes. Okay. Now I will really finish this Zoom call because I have to set up the system for the next one.
Thank you for the lecture.
Yeah. Okay. Have a good day. Those who don't need elementary mathematics, those who do, I will see you soon.
Madam.
Thank you, Ms. Bang.
Hello.
Yes, what?
Madam, I passed the elementary mathematics test, but in just 2 weeks.
If you pass the elementary mathematics test, then you do not have to write. Then you do not have to write the elementary mathematics unit tests.
Okay.
That's of course, you are not required to do this. You may do this for your own purposes, for your own sake, to check yourself, because I will mark it regardless. But I have people, let's say people who are required to do elementary mathematics are separated in my list. So I know who is required and who is just attending. So that's not a problem. If you have passed elementary mathematics, it shouldn't be a problem. Well, I would advise you to write the test just to check yourself. But apart from that, it's not required.